Welcome back to the podcast. Today, we're diving into the intricate world of databases, focusing on a fundamental aspect of database management, transactions and concurrency control. We'll break down some complex concepts such as serializability and two-phase locking and explore how these systems ensure data integrity while maximizing performance. So, grab your headphones and let's get started. Let's begin by unpacking what transactions are in the context of databases. At its core, a transaction is a sequence of operations that are executed as a single logical unit of work. The primary goal here is to ensure that all operations within the transaction either complete successfully or fail as a whole, thereby maintaining the integrity of the database. One interesting method for managing transactions is through the use of stored procedures for replication. Instead of copying transaction rights from one node to another, databases like VaultDB execute the same stored procedure on each replica. This approach requires that stored procedures be deterministic, meaning they must yield the same results when executed on different nodes. For example, if a transaction relies on the current date and time, it needs to use specific deterministic APIs to prevent any discrepancies. Now let's delve into concurrency control. One way to simplify this is by executing all transactions serially, but this can limit throughput to the speed of a single CPU core. While read-only transactions can be executed elsewhere using snapshot isolation, high write throughput applications often face bottlenecks. If a transaction needs to access data that isn't currently in memory, one potential solution is to abort the transaction, fetch the data asynchronously, and then restart it once the data is ready. This technique is referred to as anti-caching. To scale beyond a single CPU core, databases can partition data. VaultDB supports this by allowing each transaction to operate within its own partition. If you can ensure that transactions only read and write data within a single partition, you can assign each CPU core its own partition, effectively scaling throughput linearly with the number of cores. However, if a transaction needs to access multiple partitions, coordination is required, which can significantly slow down performance. In fact, VaultDB reports a throughput of about 1,000 cross-partition writes per second, which is a stark contrast to its single-partition throughput. As we consider transaction execution, we encounter the concept of serializability. This is a strict form of isolation that ensures transactions appear to execute in a serial order even if they run concurrently. To achieve this, every transaction needs to be small and fast. A single slow transaction can stall the entire processing system. Additionally, the active dataset must fit into memory, as accessing data from disk can lead to significant slowdowns. One traditional method for ensuring serializability is two-phase locking, or 2PL. It's important to differentiate this from the two-phase commit protocol, as they serve different purposes. In 2PL, locks are employed to prevent dirty writes. If two transactions attempt to write to the same object, the lock ensures that the second writer must wait for the first transaction to complete. This mechanism allows multiple transactions to read the same object concurrently, but exclusive access is required for writing. The two phases in 2PL involve acquiring locks during the transaction execution phase and releasing them at the end. However, a significant downside of 2PL is its impact on performance. It can reduce concurrency because transactions may have to wait for others to finish, leading to potential bottlenecks. This is particularly problematic in traditional relational databases that are designed for interactive applications, where long wait times can occur. Another challenge in 2PL is the occurrence of deadlocks. This happens when two transactions are waiting on each other to release their locks. Most databases can detect deadlocks and will abort one of the transactions to allow others to proceed, but this can lead to wasted effort if the aborted transaction needs to be retried. Let's also touch on the issue of phantoms, which can arise in serializable isolation. A phantom occurs when one transaction alters the results of another transaction search query. To prevent this, databases must implement predicate locks. These locks ensure that if one transaction is querying for specific data, no other transaction can insert or update data that would impact that query until the first transaction is complete. However, checking for matching locks can be time-consuming, which has led many databases to adopt a simplified version known as index range locking. This method allows for more efficient locking by approximating the range of objects affected by a transaction, helping to maintain performance while still providing a level of isolation. To wrap up our discussion, let's highlight some key takeaways. First, stored procedures enhance replication efficiency, but require deterministic outcomes. Second, while serial execution simplifies concurrency control, it limits throughput to a single CPU core. Third, partitioning allows for scaling by enabling independent transaction processing across multiple CPU cores. Fourth, two-phase locking provides strong isolation but can lead to performance issues and deadlocks. Lastly, predicate locks are essential for preventing phantoms and ensuring data integrity during concurrent transactions. In conclusion, understanding transactions and concurrency control is vital for anyone working with databases. We've explored how various approaches can impact performance and data integrity, from the simplicity of serial execution to the complexities of two-phase locking. As databases continue to evolve, the balance between performance and consistency will remain a critical focus for developers and database administrators alike. Thank you for joining us today. We hope this discussion has provided some valuable insights into the fascinating world of database transactions. Don't forget to subscribe for more in-depth explorations of the technology that powers our digital lives. Until next time, keep exploring.